To overcome this challenge, an alternative method was devised, which included the assembly of a track girder and the use of counterweights to accommodate the curved girder. Launching. Initially, the track girder was assembled with a bent structure in the yard behind P3. A 120-ton all-terrain crane was employed to connect the girders on the bent structure. Once the track facilities were completed, the overhang equipment and connecting structures were assembled and connected, forming 4 blocks of the girder. A launching of approximately 23 meters was performed, which involved pushing the girder forward using the trolley system. After the initial launching, the remaining 5 blocks and the rear overhang equipment were connected. To accommodate the curved direction of the girder, the overhang equipment was cleverly bent at the joint. Additionally, since the girder was curved, there was a constant force trying to make it fall towards the outside of the curve. To counteract this force, a 30-ton counterweight was installed on the girder to provide resistance. The position of the counterweight was adjusted as the launching progressed. On December 14, a road closure was implemented below the P to P3 section to facilitate the movement of the overhang equipment to reach J4 on the P1 side. This allowed for uninterrupted progress during the launching process. At the P2 and P1 piers, launching devices such as vertical jacks, horizontal jacks, and mound jacks were installed. A slide base, horizontal jack 30 tons, and clamp jack were placed behind the girder, creating a trolley system that supported the launching with 2 initial support points, which later became 3 support points after reaching the P1 side. The launching process involved moving the girder forward in increments. The standard distance launched was 1 meter, and it took approximately 8 minutes to complete. After each 1-meter launch, the girder underwent mound operations, and then another 1-meter launch was carried out. After launching 13 meters, the first counterweight movement was performed, which took about 30 minutes. Following this, an additional 8 meters were launched, and the overhang equipment reached J4 on the P1 side after a M. Once the overhang equipment reached J4 on the P1 side, the second counterweight movement and jacking up on the P1 side were executed. This was followed by a 6-meter launching to reach the designated position. In total, the construction and assembly process involved launching the girder in increments and adjusting the counterweight position to ensure the successful erection of the curved girder. By implementing this alternative method of assembling a track girder and utilizing counterweights, the construction team was able to overcome the challenge posed by the curved girder without obstructing the waterway or using additional structures in the river. The Sakura Marai Bridge route was successfully built, providing a vital crossing for the Daioka River.
The Tumblr Bridge, an iconic steel structure that has spanned the river, had served as a vital connection for both road and boat traffic. However, due to its age and corrosion, the opening section of the bridge had deteriorated significantly and needed urgent replacement. The first step involved the removal of the old section of the Tumblr Bridge. Workers began by dismantling the wooden deck of the bridge, along with some outdated equipment. Once the deck was cleared, the bridge was rotated 90 degrees from its standard position to rest firmly on the ground, facilitating safe removal. Using oxyacetylene torches, the bridge was meticulously cut into manageable sections. These cut segments were then carefully lifted and removed from the site. Proper disposal ensured the safety of the environment and surrounding areas. Some of the old equipment salvaged from the bridge was found to be in good condition. Engineers opted to refurbish these components, promoting sustainability and cost-effectiveness in the replacement process. A crucial aspect of the Tumblr Bridge's design is its pivoting mechanism, enabling it to open and allow boats to pass through. The replacement project necessitated installing a new main bearing on which the bridge would pivot. A 500-ton mobile crane was brought to the site and positioned for the lifting phase. With the main bearing in place, engineers carefully aligned and fitted the two halves of the bearing mechanism. Precision was paramount to ensure the smooth pivoting of the bridge during operation. The engineering team employed advanced measuring and alignment techniques to ensure a perfect fit. Each component was carefully positioned and adjusted to maintain uniformity and eliminate any potential friction points. The successful alignment and fitting of the main bearing mechanism were crucial milestones in the replacement process, as they laid the foundation for the Tumblr Bridge to operate seamlessly, enabling it to open and close smoothly, accommodating boat traffic with ease and ensuring the continued functionality of this historic steel bridge for generations to come. Once the bridge was correctly positioned on its main bearing, concrete was added to the rear section of the structure to act as a counterbalancing weight. This step was crucial to maintaining the bridge's stability during opening and closing. To protect the bridge's steel surface and enhance its longevity, a specialized coating was applied. Unlike the old bridge, which had a wooden deck, the new Tumblr Bridge received a durable steel surface coating. With the main structure complete, the final installation and testing of the hydraulic mechanism began. This system consisted of 4 hydraulic wedges that supported and aligned the bridge during regular traffic operation. Engineers retracted the wedges, allowing the hydraulic motor to turn the gear wheel and pivot the bridge gently to its open position. This remarkable single-span structure now officially holds the title of the Midland's longest railway bridge, boasting a towering clearance of 92 meters beneath its arch, strategically designed to accommodate future HS2 tracks and pave the way for zero-carbon trains to access the upcoming depot in Washwood Heath. During Easter, the old viaduct and tracks were demolished, making way for the massive 2,600-ton railway structure, which was successfully put into place at the beginning of May. Subsequently, a race against time commenced to reinstate the tracks, leading up to this momentous day that saw the reopening of the Stekford to Aston freight line, a vital link to Birmingham's Freightliner terminal. The accomplishment of the past 23 days in rebuilding and closing the SAS Bridge to traffic has been a massive achievement for the team involved. The new bridge, with its iconic design that seamlessly blends into the industrial ambiance of the area, is expected to stand for over 120 years, becoming a symbol of East Birmingham's railway revolution. The first train's successful passage not only demonstrates the engineering prowess behind the project, but also signifies a major step forward in the region's transportation infrastructure. The Vodafone Arena Stadium, located in Istanbul, Turkey, is a masterpiece in the making. Its crowning glory, the roof's inner ring, is being meticulously lifted inch by inch at a steady pace of 3 meters, 10 feet, per day. This precision operation is expected to be completed in a week, after which it will be connected to 84 outer columns to ensure stability. The inner ring alone weighs a staggering 850 tons and has taken nearly half a year to assemble. Once in place, the inner ring will complement the 84 outer columns, forming a robust structure with a total weight of around 2,500 tons. This colossal engineering feat will stand tall above the stands, accommodating almost 42,000 spectators. The stadium's capacity is further enhanced by 144 executive boxes, the 1903 lounge with space for 1,903 spectators, and the 1903 stand, which can house 636 fans. Moreover, the stadium boasts a spacious restaurant covering an area of 2,123 square meters, a rooftop restaurant spanning an impressive 2,520 square meters, and a VIP parking lot accommodating up to 600 cars. Beyond its physical attributes, the stadium prides itself on being a smart stadium, integrating modern technologies to enhance the fan experience. Utilizing Stadium Vision and high-speed Wi-Fi technology developed in partnership with Cisco, fans can immerse themselves in a technologically advanced environment.
The construction process of the Sakura Mirai Bridge route involved the unique challenge of building a curved girder without obstructing the waterway or using a bent structure in the river.
Q2 Stadium, located at 10,414 Chle Place in Austin, Texas, is a state-of-the-art soccer-specific stadium with an approximate seating capacity of 20,500. The stadium is the home ground for Austin FC, a professional soccer team, and was constructed at a cost of around $260 million. Precourt Sports Ventures, the team operator, took on the responsibility of privately financing the entire construction project. The stadium site spans 24 acres and includes various features such as green spaces, potential housing options, and mixed-use retail facilities. The project was initiated in March 2019 when Precourt Sports announced Austin Commercial as the construction manager and Gensler as the lead architect. The groundbreaking ceremony for Q2 Stadium was held on September 9, 2019. To accommodate the stadium, the site had to undergo rezoning, which was successfully passed by the Austin City Council on June 6, 2019. Subsequently, on August 19, 2019, the City of Austin approved the site plan for the stadium in North Austin. One of the significant milestones in the stadium's history was reached in January 2021 when Austin FC entered a naming rights partnership with Q2 Holdings, a local online banking provider. As a result, the stadium was officially named Q2 Stadium at Chle Place. The stadium offers a mix of seating types, including traditional seats and safe standing areas, providing a diverse experience for soccer fans. Its field size is 115 yards by 75 yards, 105 meters by 69 meters, with a lush grass surface for players to compete on. The Al Thummama Stadium in Qatar is an awe-inspiring testament to modern architectural design and engineering expertise. Conceived by the renowned architect Ibrahim Jada, the stadium draws inspiration from traditional taqiyya hats, reflecting cultural heritage and significance in the Arab world. With its brilliant white exterior and circular form mirroring the Ghafiya cap, the Al Thummama Stadium stands as a symbol of dignity, independence, and unity in the region. Located strategically near the Hamad International Airport, the stadium offers easy accessibility for visitors from around the globe, making it an ideal world-class venue. Its proximity to major transportation hubs enhances the convenience for spectators attending events hosted at the stadium. One of the most remarkable aspects of the Al Thummama Stadium is its unwavering commitment to sustainability. Throughout its construction, the project adhered to sustainable practices, utilizing energy-efficient materials and implementing efficient waste management systems to minimize its environmental impact. Qatar's emphasis on environmental consciousness is further exemplified by the stadium's cutting-edge advanced cooling tech system, which is powered by solar radiation processing. This system not only maintains a comfortable temperature for players and spectators, but also improves air quality, showcasing Qatar's dedication to eco-friendly practices and leaving a positive impact on the environment. The stadium was completed in preparation for the much-anticipated 2022 FIFA World Cup, with the capacity to accommodate 40,000 spectators. However, the Al Thumama Stadium's legacy extends beyond the tournament. In a noble gesture, half of its seats will be donated to other countries after the event, emphasizing Qatar's commitment to promoting sports infrastructure globally and fostering a sense of unity and collaboration. Following the World Cup, the stadium's capacity will be reduced to 20,000 seats by dismantling the upper tier. This decision is a strategic move that ensures the site's efficient and versatile use even after the tournament. The stadium will then be repurposed to include a state-of-the-art sports clinic and a boutique hotel, further enriching its legacy and contributing to the development of sports and healthcare infrastructure in the region. This demonstrates Qatar's foresight and dedication to utilizing resources responsibly and making a lasting positive impact on its community. As Qatar approaches the World Cup, meticulous attention to detail and a paramount commitment to safety, technology, and spectator comfort are evident in the final preparations of the Al Thumama Stadium. The organizers have spared no effort in ensuring that the venue provides an unparalleled experience for players and fans alike. Cutting-edge technology has been integrated throughout the stadium, enhancing the overall experience of those in attendance. The stadium's design also prioritizes safety, with robust security measures in place to ensure the well-being of all visitors. Qatar's dedication to ensuring a secure and enjoyable environment for all reflects the nation's commitment to hospitality and creating a memorable experience for its guests. With its state-of-the-art facilities and sustainability-focused initiatives, the Al Thumama Stadium stands as a symbol of innovation and progress in the Arab world and beyond. It serves as a beacon of cultural heritage and significance, showcasing Qatar's rich history and traditions to a global audience. The Chle Flying Arches, a historic railway viaduct located in Chle, has been an engineering marvel since its construction in the 19th century. However, over the years, the viaduct has faced challenges due to aging infrastructure and increased traffic demands. To ensure the continued safe and efficient operation of the railway, a comprehensive renovation project was undertaken. The removal of 16 aging stone arches marked the initial phase of a challenging yet crucial restoration project. These arches, standing as architectural relics, had endured the test of time, but years of exposure to the elements and natural decay had taken their toll. It was imperative to address their deteriorating condition to preserve their historical significance and prevent further damage. Their paramount concern was to safeguard the historical and cultural importance of the structure. Every step was taken with the utmost care to ensure that the arches were dismantled without compromising their integrity. Each arch's unique design and construction materials were taken into consideration to minimize potential damage during disassembly. Cranes and specialized equipment were utilized to handle the heavy stones safely. As the arches were disassembled, reusable stones were set aside for future conservation endeavors. These salvaged stones would either be restored and reinstated to their original locations or utilized in the construction of the new design, ensuring a seamless integration of history and modernity. Following the delicate removal of the 16 aging stone arches, the next crucial step in the renovation project was to ensure the structural stability of the viaduct During the restoration process, giant cranes and other heavy machinery were brought to the site to facilitate the lifting and placement of the steel arches. This is where a Hessel fork truck might have played a crucial role. Given the forklift's capacity for heavy lifting and maneuverability, it could have been employed to transport smaller components of the steel arches and assist in their assembly. The forklift's forks could be adjusted to accommodate the different parts, and its counterweight would ensure stability during the lifting process. The temporary steel arches were carefully positioned in place and secured to the existing structure using heavy-duty bolts and welding. Once the new temporary steel arches were in place, engineers conducted thorough load tests to ensure their strength and suitability for the ongoing railway operations. The temporary structures were expected to bear the heavy loads and dynamic forces imposed by passing trains without compromising the safety of passengers and the integrity of the viaduct. While the temporary steel arches served their essential purpose during the renovation period, they were designed with an understanding that they would eventually be replaced by permanent stone arches. The temporary phase allowed for necessary restoration work on the viaduct's original stone arches and the installation of new, accurately crafted stone components. The installation of new temporary steel arches showcased the seamless integration of modern engineering expertise with historical preservation efforts. It served as a testament to the commitment of the team to uphold the viaduct's heritage while ensuring its continued function and safety for generations to come. The combination of temporary steel arches and a Hessel fork truck's assistance during the dismantling phase exemplifies the synergy between cutting-edge machinery and traditional craftsmanship in the realm of restoration projects. With the temporary steel arches in place and the ground anchors securing the foundations, the final phase of the project involved the replacement of the original stone arches with modern, durable steel arches. The decision to replace the stone arches with steel arches was driven by the need for a more robust and low-maintenance structure that could withstand the demands of modern railway operations while preserving the historic character of the viaduct. The new steel arches were meticulously designed to replicate the original architectural features, paying homage to the viaduct's rich heritage. These arches were carefully lifted into position and permanently secured, marking the completion of a truly transformative engineering feat. One of the key challenges faced during the project was stabilizing the viaduct's foundations. To achieve this, an extensive ground anchors installation was carried out. A total of 320 ground anchors were strategically placed to reinforce the viaduct's stability and prevent any potential subsidence issues. The anchors were designed to distribute the structural loads effectively, enhancing the overall strength and longevity of the viaduct. A significant aspect of the renovation project involved the installation of 800 meters of trench sheeting. Trench sheeting served multiple purposes, providing temporary excavation support during the arch removal process, reinforcing the embankment for improved stability, and facilitating the subsequent drainage and track renewal works. Drainage improvement was a crucial aspect of the project, ensuring the viaduct's resilience to adverse weather conditions and mitigating the risk of water-related damage. Over 450 meters of drainage systems were installed along the viaduct's length to efficiently redirect rainwater and prevent pooling. Additionally, the track renewal process was carried out simultaneously. The existing tracks were carefully removed, and the trackbed was meticulously prepared for the installation of new tracks. The track renewal not only improved the overall performance of the railway, but also ensured smoother and safer journeys for passengers and freight.
The construction of the Cypress Gardens Bridge involved the use of high-quality concrete to create an all-concrete structure. The bridge was designed with a single span, measuring 117 feet in length, providing ample clearance of over 100 feet between the abutments. This design was intended to accommodate the flow of water and mitigate the risk of flooding during heavy rain and storms. The process of setting the bridge girders began on July 31, 2014, as part of the construction schedule. The girders used in this project were carefully selected and designed to withstand the load and stress placed upon them. These girders are typically made of reinforced concrete, which provides excellent strength and durability. Setting the girders required the use of heavy machinery. Crane operators played a vital role in this process, as they were responsible for carefully lifting and placing the girders into position. The girders were manufactured off-site and transported to the construction site, ready to be installed. Before setting the girders, the construction crew ensured that the bridge abutments were prepared to receive the girders securely. This involved constructing solid foundations and properly aligning the abutments to support the weight of the girders. The abutments were also reinforced with steel and concrete to enhance their stability. Once the abutments were prepared, the crane operator carefully maneuvered the crane into position. The girders were lifted using the crane's powerful lifting mechanism, which allowed for precise control and placement. Each girder was positioned according to the predetermined layout and alignment, ensuring proper fit and support. As each girder was set in place, it was temporarily secured to the abutments using specialized clamps or brackets. This provided additional stability during the subsequent stages of construction. Once all the girders were in position, the construction crew meticulously checked their alignment and made any necessary adjustments to ensure a precise fit. With the girders securely set in place, the next step in the construction process was to pour the cast-in-place reinforced concrete bridge decks. These decks serve as the road surface and provide a smooth and durable driving surface. The bridge decks were carefully formed and poured over the girders, creating a seamless connection and ensuring structural integrity. Upon unloading the bridge erector from the girder truck, it is essential to assess its position. Carefully observe if any adjustments are required to ensure proper alignment and stability. This evaluation helps prevent any potential issues during the removal process. Before proceeding, it is crucial to evaluate the presence of crosswinds. Crosswinds can affect the stability of the bridge erector, making it unsafe to proceed. If crosswinds are present, it is advisable to wait until the conditions improve or take necessary precautions to mitigate the risks. Once the assessment and crosswind evaluation are complete, the bridge erector can be advanced a little further, if required, to allow space for the subsequent steps in the removal process. To facilitate the removal process, prepare the front legs of the bridge erector. Ensure they are positioned correctly and securely before proceeding. This step helps maintain stability and safety during the subsequent stages. The unloading and resetting of the bridge erector can be a time-consuming process, often taking several hours to complete. This crucial step involves meticulously following the manufacturer's instructions to ensure proper functionality and readiness for the next operation. While removing the girder truck, it is essential to ensure that the area is clear of any obstructions or vehicles. Coordinating with the team and communicating with the car behind the girder truck is crucial. Once the path is clear, the car behind can drive away after a brief wait. To remove the girder truck, the master of the operation proceeds by removing the shelf from the truck and neatly placing it aside. Cooling mechanisms, such as fans, may be utilized during this process to ensure the equipment remains at an optimal temperature. Throughout the removal process, it is essential to maintain a secure environment. Security fences can be erected to establish boundaries and prevent unauthorized access. Strict adherence to safety protocols helps minimize the risk of accidents and injuries. During the removal process, the bridge erector is supported on the moon car, which ensures stability and maneuverability. Additionally, the provided material highlights the low fuel consumption of the grain truck, thanks to its small fuel tank. This eco-friendly feature contributes to cost efficiency and sustainability.
The first step is the careful selection of high-quality structural steel for girder fabrication. Engineers consider factors strength, ductility, and corrosion resistance when choosing the appropriate steel. The selected steel typically adheres to relevant national or international standards to ensure the bridge's integrity. Once the steel plates or sections are obtained, they are cut to the required dimensions. Automatic cutters, plasma cutters, and lasers are used for this purpose. These machines offer precision and accuracy, ensuring that the steel components are cut according to the specified design. Welding is a crucial process in steel girder fabrication. The welds must meet specific standards and undergo non-destructive testing, NDT, to verify their quality and integrity. NDT methods, such as ultrasonic or X-ray testing, are employed to ensure the welds are defect-free. After assembly, the steel girder undergoes surface treatment to enhance its durability and protect it from corrosion. Processes like shot blasting are employed to remove impurities from the steel's surface. Protective coatings, such as primer, paint, or galvanizing, are then applied to safeguard the steel from environmental elements. During on-site assembly of the SD steel deck arch cantilever girder, a careful assembly order is followed, taking measures to prevent damage to the pre-stressed tendons. On-site welding is carried out meticulously, adhering to protective facilities that meet construction regulations. The SB arch cantilever girder offers weight reduction of approximately 30% compared to precast box girders. This advantage allows for installation using a single crane without the need for a temporary support system. This streamlined installation process helps expedite construction and reduce costs. The installation process involves the careful installation of bolted joints according to the construction type to ensure safe and secure assembly. Once the precast panels are installed, concrete is poured up to the pre-installed stoppers inside the SB arch cantilever girder. Initially, The Suyang River Bridge was planned to be constructed using the PCT composite construction method in 2014. However, due to collapse and appointment accidents at other construction sites using this method, the Korea Expressway Corporation (KEC) and the Korea Construction Cost Management Corporation (KCC) had to explore alternative design methods. Despite their efforts, they were unable to find a suitable installation method within the construction period for the 80-meter-long bridge. After completing the final pavement work without closing the road, strict quality management is implemented. Exposed concrete surfaces are covered with curing materials to protect the concrete and ensure its durability. Eventually, the Haedong Bridge, which had proven expertise in SB arch construction, was selected as the designer for the Suyang River Bridge. The construction site was opened in July 2016, and within 3 months, the construction of the 9-span bridge, including assembly, was completed.
The art of tunnel construction has been an integral part of human civilization for centuries, from ancient subterranean aqueducts to modern transportation networks. Tunnels have played a vital role in connecting people and facilitating the movement of goods. Beneath our feet, a fascinating journey unfolds as massive machines, known as tunnel boring machines, TBMs, dig through the Earth's crust, overcoming geological challenges and urban complexities. In this article, we delve into the operation of these colossal TBMs and the remarkable expertise of Bouygues Travaux Publics in underground construction. When it comes to tunnel construction, versatility is key. Different terrains, depths, and geological conditions demand adaptable tools, and the tunnel boring machine fits this bill perfectly. TBMs are engineered to handle a wide range of scenarios, from shallow trenches to hard rock, making them an indispensable asset in the realm of underground construction. A tunnel boring machine is a behemoth weighing several thousand tons, resembling a moving factory designed specifically for the excavation process. These machines are custom-built to suit the unique requirements of each project, ensuring optimal performance and safety. At the forefront of the TBM lies the cutting head, equipped with robust discs that gradually dismantle rock and disintegrate earth, sand, and other materials. As the cutting head does its work, the excavated materials are transported away through a sophisticated system. In some cases, slurry is created and sucked into pipes for disposal, while in most instances, a screw conveyor efficiently handles the transport of materials for further processing, recycling, or storage. To construct a tunnel, it's essential to have a sturdy structure that can withstand pressure and provide stability. This is where the ring segments come into play. Approximately every 2 meters, the TBM places a ring of segments closest to the excavation site. The production of these segments adheres to strict standards, with the concrete composition tailored to the specific constraints of each project. When assembled into a ring, these segments create a pressure-resistant tube, forming the foundation of the tunnel. The operation of a TBM is not a straightforward process. The TBM operator is a skilled professional who guides the machine through the terrain, anticipating its behavior during excavation. This is made possible through an in-house developed guidance system that provides precision down to the millimeter. Supported by the geometry of the ring segments, TBMs can navigate a 3-dimensional, winding path, adapting to the ever-changing geological conditions. Tunnel excavation is a remarkable adventure filled with challenges and uncertainties. Unlike above-ground construction, there's no detailed plan of the underground world. Geological conditions and existing structures can create unforeseen obstacles that must be managed with extreme precision, particularly in urban areas. In loose or mixed terrains, a confinement pressure is constantly applied to the excavation chamber to prevent water ingress and support the ground before placing the segments. Maintenance within the TBM's head is conducted under hyperbaric conditions, akin to deep-sea diving, demanding extreme caution to ensure the safety of personnel. Safety is paramount in tunnel boring operations. The expertise developed in this field not only ensures the well-being of the personnel inside the TBM, but also allows for deeper excavations and the exploration of new possibilities in urban areas with existing infrastructure. Innovation is a driving force behind the evolution of tunnel boring technology. Technical teams, in collaboration with manufacturers, continuously improve TBM design and performance. They patent monitoring tools, maintenance robots, machines for deconstructing existing tunnel segments, and optimize additives and concrete to push the boundaries imposed by the laws of physics. These innovations enable the realization of the most imaginative demands of clients, demonstrating the capacity to adapt and thrive in the ever-evolving world of tunnel construction. Bouygues Travaux Publics stands as a global leader in underground construction, with a rich history of successfully tackling diverse tunneling projects across the globe. With over 500 kilometers of tunnels bored, world records set, and a commitment to innovation, their technical prowess and unwavering dedication to safety have propelled them to the forefront of the industry. In a world where the movement of people and goods remains pivotal, the expertise of Bouygues Travaux Publics and the incredible capabilities of tunnel boring machines ensure that tunnels continue to be the arteries of connectivity, transcending geographical, geological, and urban challenges. As they pose the question, "Are you ready?" one can't help but marvel at the immense potential that lies beneath the surface, waiting to be unearthed by the next generation of tunnel visionaries.